Thank you for the opportunity to give this talk. It's been a while. So I'm myself a research scientist at Sorbonne University. I'm mainly working on deep learning, and in particular, I'm very interested in theoretical properties of deep neural network. For example, to understand how to open the black box of neural network. So I got a background more in signal processing, but something I really find super exciting about deep learning is that it's really at the intersection of many fields, like optimization, statistics, harmonic analysis in my case. There are many ideas around deep learning, and it's super exciting also because there are many new results, many new engineering methods that allow us to get some super impressive applications. And during this talk today, I intend to first kind of describe the applications of deep neural network in some context, so in particular in the context of supervised image classifications and these kind of things. So first of all, I will try to introduce you to the image classification from a signal processing point of view. So then we will see how with deep neural network you can solve some very high-dimensional task, literally solve, that's the appropriate word. And so in a second time, I will discuss several interpretability results. So progressively it will become a bit more mathy in some sense. So the second part of the interpretability will be about the scattering transform, which is basically a neural network where there is no learning, which is only built from some wavelet transform. And finally, I will discuss several statistical learning results that really shed light on neural networks. So in particular, optimization guarantees, generalization, and some approximation properties and kind of things. Okay. So I'm just going to mention the lab because in some sense there are some clues for tomorrow which are kind of disseminated in the presentation. So tomorrow we will try to design some invertible neural networks with PyTorch and kind of things. Then we will have a notebook about the scattering transform. And well, if we have some time, we will try to play with some pre-trained models and these kind of things. Okay. Right. So image classification. So I like to start with a take-home message slide. Who has seen this kind of slide? I mean, already. I mean, in some class, in some lectures. So I guess more or less everybody, right? Okay. So can you kind of tell me why this slide is pretty misleading? So when you see this slide, it kind of looks like this is a good example of a classification task where you have different colors, different points which have different colors. And the goal is to guess the color of a new point. So my question is, why is this slide, actually, this picture is super misleading? Has someone any ideas? Yes?
Because there's only 2 dimensions, and in reality there's so much more, and we can make the same conclusions about the data, everything is far away.
Oh, I should have.
Sorry, we do it again?
Because here there's just 2 dimensions, and in reality the data lives in a much higher space and higher dimensional space, and we can just make the same conclusions about seeing the data like this.
Absolutely. So, I mean, I both like and dislike this slide because, in some sense, it's a very simple way to formalize what is a supervised classification task. On the other hand, yeah, we're not facing the high dimension. So, if you're trying to, so that's some pretty classical things, but I really like to go back to the basics. So if you're working in high dimension, so as you know, if you want to estimate a PDF, what you normally do is that you do a histogram. You try to estimate the number of points that will fall in some bins of the histogram, and then with some regularity assumptions, you're going to be able to draw the PDF. And as you know, if the dimension is increasing, then suddenly most of the bins are empty, and this is what we call the curse of dimensionality. So it occurs in many machine learning problems. I mean, I would say most of them. In the previous task, what was what was super easy about it was the fact that we were working R2, as you said, and supervised classification. It does consist in trying to build a representation phi of the data. So in some sense, training model phi on some training set to estimate some label of the data. And then we validate a model on some test sets. So that's how you basically design a pipeline, for example, for some prediction tasks, some regression tasks, some classification tasks, and all these kind of things. And the best setting was the one that we saw in the previous slide, which means that when the dimension of x is small, the dimension of y as well is small, like the label, and the data set is large, when you have many available samples. So there are many types of supervision. And I think it's kind of like good to have them in mind, because most of machine learning problems are summarized here, and it gives some highlights, some intuitions on what you could do later. So the one I will discuss now is definitely supervised learning, but people are also interested in unsupervised learning. So you have no labels. They're interested in semi-supervised learning, when you have some labels which have, some samples which have some labels, some samples which have not. Some weakly supervised learning, where you're not sure of the quality of the labels. Some self-supervised learning, so we're here. It's basically an unsupervised learning setting which is casted as a supervised problem. And then there is like the multitask, transfer learning, and all these kind of things. And so if you want to address, for example, a simple task like digit classification, in general, what we do is that first, we propose a model of our data. So in the case of digits, so for example, MNIST, your data, they have mostly some variability which is geometric. So what I mean by that is small deformations or translations. So once you got a nice model of your data, you can design a representation where your goal is to reduce those variabilities, like the geometric variabilities, in order to just have a simple complexity problem, which means that if you have enough samples, then you can have a good estimate of your representation. And for example, a good candidate would be the scattering transform, because the scattering transform will achieve some translation invariance, and as well, some will be stable to deformation. And then you can propose, for example, a convex classifier to separate your data. So for example, in your SVM, and then if you combine your SVM with the representation, you project your data, and then you're able to separate them. So the unfortunate thing is that in general, you just get some reasonable performances. Like you will get something which is good, but which is not the state of the art. And in the following, I will discuss some machine learning models, so the deep neural networks, where you don't have any models for real images, which means that you have some giant data sets, but you have no idea how you can mathematically model them. You don't have much a priori. Maybe you got translation variance, maybe rotation covariance of your image, which means that if you see two cats and they're translated or rotated from each other, then you can guess they have the same label, but that's almost all you can say. You will learn almost every parameters of your problem. And however, here, we will obtain the best performances. And I think what is really striving is those methods that most of the time we have absolutely no reason of why they're working. And that's what makes them very interesting, I would say. So before like to go directly in the method, I think it's nice to look at the data first. So if you consider, for example, a data set like ImageNet, so that's the standard data set which is used in deep learning. So it does consist in 1 million images. So it's super big, as you can see, like several gigabytes. You have a bunch of test images, like 400,000. And most of the images, they are large and pretty various. So for example, you can find some cartoon images. You can find some natural images, which follows natural statistics. There's definitely like many different types of images that does correspond to a given label. And the way they are labeled is via human collaboration. So basically, like you can imagine that you have a bunch of people, they're gonna watch those images the whole day, and they're gonna click like, okay, this is a cat, this is a dog. So you said some people who are labeling the images, also it means that there's some kind of bias which are incorporated. So of course, like you try to unbias your data set, so you continuously you try to clean your labels. So you apply this procedure, and you try to remove the labels that have the wrong. You remove the samples that have the wrong labels. However, it's not because like the labels are clean that the task is simple. And the reason why like image classification is a difficult task, so it's mainly because you have some geometric variabilities. So as I said, translation, rotation, scaling. So you can also think in terms of like luminosity. So when you vary the contrast of your image, or also occlusion, when you, for example, you put an object in front of another object, those kind of things. And also like small deformations. So the nice thing about all this stuff is the fact that you have an explicit way to express those variabilities. I mean, like, rotation of an image, you can definitely like write it. It's some linear operation. So this is nice because it means that we can definitely find a way to handle those variabilities. On the other hand, when you look at a given class, see that there are many intraclass variability, which is super hard to model, right? If you look at those pictures, you see that there is no clear formulation that will allow us to be like, okay, this is this label because of a given reason, except the fact that we can, mentally see it. And there are also pretty much like many extra class variability. So in some sense, I mean, it's not in some sense, there are many variants, and the goal is to reduce the variance of our problem. The data, they are living in a super high dimensional space. And what we want to do is definitely to reduce the size of the space, because like it's already big, everybody is far from each other. And the way people have found to achieve this kind of properties to go through some representation. So for example, some properties you might desire in your presentation will be to be invariant to some group of variability. So as I said, translation, rotations, kind of things. You might be willing to be stable to noise, which means that if you add an additive noise to a signal, you would like that the representation will behave nicely with respect to the symbol. So the simplest way to achieve this is, for example, to be Lipschitz. In some cases, you might want to be invertible, because it means that you don't have discard any structures or attributes of your signal. And very often, you can cast it in a different way, but you might want to be linearly separable. So if you try to do that, to handcraft it, it's going to be hard, right? Given the task, it's very unclear what to do, except if you're in the setting of those small digits. And the very interesting thing is that after several years of research, I really like this comic. So people have tried like a bunch of methods. They really tried to engineer like many pipelines with their data, and at some point they got the answer. And the funny thing is that it was given like by those neural networks, and so now I'm going to review like several tasks which are completely solved by the neural network. So it's very impressive. I mean, when you look at the benchmark and what they do, it's really like striking. So if you look at like now, if you look at the papers which are published now in deep learning, most of them they come like from several companies like Google, DeepMind, Facebook. So it's a bit like strange in some sense, because like when you're from academia, you're more used to like research papers which are from universities. And so as I said, like deep learning has this ability to solve, literally solve, high-dimensional problems, which seemed impossible before deep learning to solve them. So it requires, in general, a huge amount of data. And the nice thing about like deep neural networks is the fact that they are generic. So literally, when you're an engineer, like you try to engineer your deep neural network, you have, very often, you don't even look at your data. You just engineer the corresponding neural network. And it's super simple to deploy, which means that it's almost the same code, almost the same pipeline, almost the same spirit. When you go for sound, when you go for text, when you go for images, and other type of signals. And the nice thing is that you don't need anymore any skills for example, designing a specific descriptor or features like MFCC or SIFT. You can forget about that. The deep neural network will learn on its own its features. So I think it's kind of necessary to understand the context of neural networks. So it's kind of a historic frame I tried to do. So it's completely biased. That's my opinion. So interestingly, like there are 2 neural winters. So I don't know what will happen in 2020, but like, you know, patterns. So in the 80s, like people were not really using neural network because it's really greedy in terms of resources. So people forget about that. However, like in the 90s, there is this interesting paper about Okun where he tried to develop like his CNN, which is often like cited for the backpropagation algorithm and kind of things. So then neural networks started to be used, for example, in a digit classification for like postal services in the US, I remember. It was Oyallon that designed the CNN to solve this kind of task. And so in the 2000, there was a kernel that showed up. And after that, people were like, yeah, why would we use like deep neural networks? There is no guarantee, and kernels are probably better. So the people started to move from the field of neural network, except for like few guys, like Oyallon, Yoshua Benjo, or Geoffroy Hinton. And the interesting thing is that together, they are kind of ignored by the machine learning community. However, they still continue to work on their neural network until it worked. And so in 2010, Geoffroy Hinton designed what is called like the AlexNet. And it's the first neural network that had some very impressive performances in a non-trivial benchmark. Like, I'm going to discuss it, but like there was really a breakthrough. And so now, I'm pretty sure you heard at least one of those. Neural networks are used with AlphaGo to literally solve the game of Go. I mean, I think now AlphaGo is the best player in the world. They are used in NLP, so with what is called a transformer, or even in GAN, which are some models to generate some signals and which have some impressive performance. So what matters in deep learning? Performance. So I told you, so there is this data set, ImageNet, which was really a super difficult benchmark in vision. So if you're doing like some computer vision, it was something, I mean, like if you wanted to handle it, first of all, you need the computational resources. And second, you need also some skills to design the appropriate like vision features. And so until 2012, you see that what was working was literally handcrafted features. So what I mean by handcrafted features, I mean like SIFT, which is basically a sort of gradients combined with some Gaussian features. And all of them, they were fed to some kind of bag of words and Gaussian mixture of models. It was working pretty fine. I mean, the accuracy was decent, but like suddenly there is this neural network in 2012, which was getting like 10 extra percent. This is gigantic, because even if even neural networks now, they only improve incrementally this benchmark. So really, like getting like 10% on it was super impressive. So it has really convinced all the community, and people decided to move in this field. And now the interesting thing is that the performance are more than superhuman, which means that, imagine if you're trying to classify yourself the images. First of all, there is 1,000 labels, which means that you have a pile of paper there, because you need to figure out which is a good label. Then you have to look at every each of the 1 million images of your data set to figure out like what was a good way to label your images. So it's super complicated. So that's why even a human will never do 100% on this benchmark. So now we can say really like the machine is better than the human. So the lack of theory. We don't know why they work well, which is a bit impressive, given the fact that they work pretty well. If you ask someone who has designed a neural network, hey, why is it working? What is the magic in the model? They will not be able to answer. So I'm sure everybody is using Facebook or something similar, and I guess you notice that now everything is automatically tagged on Facebook. So most of that is due to some neural network just especially designed for faces. Just get the state of the art on that. So it's very good. Like you get some very good performances on this kind of things. Some other tasks, for example, coloring images. Here, interestingly, like the output is super high dimensional, and still the neural network is pretty good at coloring images. So what you do is that you feed some black and white images. I mean, doing this data set is pretty trivial, right? Because you just take a colored image and you make it black and white. You train your model, and then you estimate the colors on some new images. It works fine. Actually, now it's really used for like movie, for coloring movies and this kind of things. More impressive, faces. So at the first glance, it looks like it's real. And then you see that there are some small issues, like some tiny details, which are like, it's not really possible. So I guess you see it now. The way those models are done, so actually there is a very funny website, it's called like thispersondoesnotexist.com. You can get more images like that. The way those images are generated is like, you have a data set of high resolution faces. You literally train your model on it, again. It learns to generate the images. So there is a notion of multiscale here, because like as you see, the images are super high resolution. And still, I think the benchmark is pretty impressive. So people are also validated, of course, that it's not only copying some faces from the data set, like there are some procedure to be sure it's a new face. But really, when you look at it, like at the first glance, it looks like super realistic. So some other super impressive like benchmarks in NLP, when you're trying to translate languages. So there is something like quite nice in that, like if you think about it. The way they do it is with an encoder-decoder. But like, basically you take any sequence of words in some language, you encode it in a sum of universal language, and then you can decode it automatically in a new, in the language you have pre-selected. But the interesting thing is the intermediary language. It means that there is some sort of like universal way to describe a text, which has been like explicited by those models, and it's a bit impressive. So I guess you can imagine the applications. For generating source code, so I don't know much C++, but like at the first glance, it really looks like some C++, and like I think even like developers will be affected by artificial intelligence, pardon. There are also those results with the game of Go. The way it worked is that actually the story of the AlphaGo is super interesting. So at first, the people were engineering some models that were using some real data. So like you had like those data set of games. You knew the issue of the game. You knew whether you're gonna win or you're gonna lose, those kind of things. And they realized after a while, so after they run their model called AlphaGo, they realized that actually you don't even need the data, and the model can learn itself to, by playing against itself, it can learn to play pretty well. And the way it's done actually is by having a tree, to explore the tree. So normally what you do is like what's the name, blue chess or something. What you do is that you explore a tree, you have some predefined feature that's some leaf of the tree. So basically you try to see, to do some Monte Carlo to see if you're gonna win the game according to which move you're gonna do. And here, instead to explore fully the tree, you put a neural network on some leaf at some depth, and the neural network will predict what will be the issue of the game. And so you iterate this idea, and with that you reinforce your neural network is gonna get better, and it's gonna, become pretty good at playing. So you need a bunch of GPU. Now it's used. So I wrote self-driving cars. I'm a bit skeptical, but people can use this kind of method in self-driving cars. But like this is definitely used in games like StarCraft, this kind of strategy, where you're exploring a tree, unrolling a tree, and trying to predict the outcome of a game with a neural network. Some other images, style transfer. So it's actually implemented in Google. So the idea is that given an image, we like to transfer the style of another image on this image. So the way it works is that you have some penalty where you're trying to match the statistics of a given image that's going to transfer the style, but you want to preserve the characteristic of the image on which you want to transfer the style. So again, you can get some super high resolution images just by using a pre-trained model on some other task. So again, the performances are a bit like something you would not be able to do for deep learning. People were trying to match some textures and match, for example, some local moments of your images by splitting it in patches and kind of things. But actually, this method works like pretty much better, right? Okay, so now let's see how you can train this kind of models. So I think the most basic and the most famous examples of model you can train is called MLP. So the idea is that you have a cascade of linear layer and pointwise nonlinearity. So it's literally like just a signal which is propagated through the cascade. So there are some, all the way of the talk I will use almost the same notation. So for me, like O is systematically a pointwise nonlinearity. I don't put parentheses because I view it as an operator. W will be some linear operator. So you see here the explicit formula, but that's just basically a matrix multiplication. And you can notice that the nonlinearity which is used will be in general like contractive, non-expansive to be precise. So there is this idea that you want to reduce the volume of the space progressively. I'm not claiming that the model is doing that. I'm just saying that it will have the possibility to implement this strategy. So this is the model that you used if you have no specific a priori. In general, people, they use it as a classifier. So it means that once you have represented your data, you're going to feed them to this MLP, and the MLP is supposed to achieve some good performance. So of course, it's non-convex, either in the input, either in the parameters. So when you train it, you're not really guaranteed you're going to reach a global optimum. And I think the most famous class of neural network now, the second most famous class of neural networks probably is the convolutional neural networks. So again, there is this idea that you will have a single image which is propagated through some convolutions. In general, the dimension of the image is progressively reduced because you're going to use some either some downsampling, some pooling, so we'll discuss that later. And to obtain some finer representation. So what's interesting is actually to view also the engineering point of view. I mean, like, so I will use some schematic figures, but like, you know, behind that there is something a bit complex with many hyperparameters that you really have to tune. So actually, we'll discuss this model. This is on AXNet. And so again, you have this formalism where you propagate like an input, so some linear layer, because the convolution is a linear operator, and some pointwise nonlinearity. And here, so I think I would just, yeah. Here, the convolution is not like, actually, when people use the word convolution, it's not precise enough. It's just a linear operator which is covariant with the action of translation. Because normally a convolution is simply you have a single kernel, you take an input signal, and then you're going to get another signal. Here, you have a collection of signals. To each signal, you're going to apply a convolutional kernel, and then you're going to sum them and obtain like a new signal. And you're going to concatenate those signals, and this is how you build one collection of channels and another collection of channels. So is it clear the way it works? Are you familiar with that, or sort of? Right. So sometimes you might incorporate some pooling, some downsampling. Again, this is non-convex. So to have a more precise view on those kernels which are used, you can view it as some very small filters. So in general, it's going to be like of size 3 by 3. For a given layer, in general, this layer is going to be downsampled. So this is what I formalized here with a 2n, like it's literally standard in signal processing. And there is a nice analogy with a Wavelet Transform, because a way to think of the fast Wavelet Transform, in particular the fast Wavelet Transform algorithm, is that you have a collection of filters which are called conjugate mirror filters, and you propagate a signal through some convolution and downsampling of the signals. And so that's how you get some wavelet coefficients at different scales. And there is really an analogy like with, because in general, the filters which are used, the conjugate mirror filters, they have a very small support, which can be of size 3, 5. And there is an analogy with the filter bank which are used by those convolutional neural networks. Yes?
Can you explain why there are the two parameters, lambda I plus 1, lambda I in your kernel?
Thanks for asking. So a given feature map, so what I call feature map is the output of a layer. It's a vector. And this vector has 2 dimensions, one which is spatial, a spatial index, and a second which is a channel index. And the idea is that you're going to apply convolution along the spatial index, which could be like with different kernels. And combining them will lead you to a new feature map. And if you do lambda I plus 1, if you have a collection of index lambda I plus 1, you will get like a new feature map indexed by this collection. This is the idea. And so there is this idea that here what you see is a single kernel which is used to build one feature map of the convolutional neural network. So it means that actually the size of the kernel will be, if it's like say 3 by 3 by gamma I, if this is the size of a single kernel and the next feature map is of size gamma I plus 1, the size of this kernel will be gamma I times gamma I plus 1 times 3 by 3. Is it clear enough with everybody? Or like, okay, cool. So, of course, the main difference with the Wavelet Transform is that the sum is not separable. Here, the sum makes it super different from a standard Wavelet Transform. You could implement a Wavelet Transform with this kind of operator, but there is a sum, so it's not. So the only thing, so people call it convolution, but actually you can just say this is a linear operator which is covariant with the action of translation. That's equivalent. Right. So people they typically use an algorithm. So I don't know why everybody is doing it. It's presenting this algorithm, but like since everybody is doing it, I'm doing it as well. It's called the propagation algorithm. Basically, just gradient descent, and that just the chain rule, which is applied to some cascade of differentiable model, and from that you get this nice formula. So there is a nice interpretation, which is the fact that you're going to propagate a signal that's going to give you an error, and you're going to get some feedbacks from the loss function, and you're going to have the ability to update your parameters from the feedback. So there is something which is like a bit bad about like this mechanism. It's the fact that except the first layer and the final layer, you will never explicitly specify what is the objective of a given layer, right? Because like everything's going to be in the black box. The way the parameters are going to be updated is in the black box of this backpropagation algorithm. On the other hand, thanks to this simple way to compute the gradient of each block of this model, you have people have developed many software like PyTorch, Keras, and these kind of things, which makes like computation of the gradient super easy. It means that instead to have to write down explicitly the formula, you can leave your software doing it for you. Everything is automatic. It's super simple, so it's great if you want to avoid writing yourself the gradient of your model. There is something bad also about like this formalism, is the fact that the layers are completely coupled. It means that if you wanted, for example, to distribute it, which would sound like natural given this graphic, you might want to train the first layer on some machines, second layer on some other machines, kind of things. Given this formalism, the model is going to be super hard to train in the distributed manner. And so the way people train their model is with SGD. So basically, you select a batch of size B of data, you compute your gradient given your loss, and you update your parameters. And so I promise this is the only slide where I will discuss that. The way it's implemented is like you split your data set in batches. So that's done on the CPU. You feed that to your model, which will be on the GPU. You get the training error, you backpropagate it, you update your parameters, and you iterate this process. Can take some hours. So people often claim that deep neural networks are slow to train. Actually, this is not true. It can be pretty fast. In general, it takes like less than 1 day to train a model on ImageNet. So this is super efficient, given the amount of data there is on this model. And there are many cooking recipes, which means that people might use some batch normalization, they might use some data augmentation, they might use something called dropout. They have to tune the learning rate. And when you look at the loss function of your model, you see that sometimes there are some jumps, nothing is smooth. It can decrease sometimes because nothing is convex. So you see that it's a very complicated black box model which is trained here. Yeah.
Could you explain what epoch means in that context?
Okay, thanks for asking. So there are many vocabulary which is specific to deep learning. For example, they call a step size a learning rate. So step size in convex optimization, learning rate in deep learning, and a full pass of the data is called an epoch. So basically, 10 epochs means that you have seen 10 times the same data, and you just complete a full epoch. It's not going something where you have a resampling strategy, where you just pick a random sample and you sample this way again independently. There is a oh, sorry. Well, so you get the okay, cool. And so. There is very often you will hear like people claiming that one of the strengths of deep learning is the reason it's working is going to be data, it's going to be computational power, and kind of things. And actually, I think when you see like 10 years after what was happening, is the fact that deep neural networks are super flexible. Means it's super easy to change the order of the block that you're going to use, to change your loss, to try some new hyperparameters. Everything is designed to be super simple to run, to launch, to train. You can adapt many hyperparameters, and the nice thing about that is that normally when you do this kind of strategy, at some point you're going to overfit, and actually in practice, and people use it in the industry, so it sort of means that it's probably working. In practice, even overfitted model, so what I mean by overfitted, I mean like they're going to achieve like a perfect score on the training set, are going to have a useful representation, which is a bit surprising, right? Because normally you expect that if you overfit on some data set, it's not going to work. That's what we're normally taught. As I said, I will just like explain one time what is a deep neural network like called AlexNet. So here it's a neural network with 8 layers. You have a first image, which is a colored image, so there are 3 channels which are propagated through the cascade. At the end of the neural network, you see that there is 1,000, an output of size 1,000, and the reason is that on ImageNet there is 1,000 classes. And so what is done in the first layer is that you apply an 11 by 11 conventional operator on your first image. That's going to give you like 48 new feature map because you're going to apply 48 different conventional kernel. In between, there is a downsampling, so that's why the resolution of the image is reduced by a factor of 4. You cascade again this idea, so here there is no downsampling, it's a max pooling instead. That's something that takes the maximum of an image over a special neighborhood. You cascade this again, and so the numbers on the which are below like 192 is the number of channels. 13 here is going to be the size of the spatial resolution of your of a given layer, and 3 by 3 is going to be the size of your conventional kernel. And you see all those numbers, so which are here. So people have tried many different ways to combine them. You can, for example, play with the number of channels that are going to be here, like the 192. There is no clear reason why you're going to use it, except that it's working slightly better. And you adapt always the number of hyperparameters that you're going to use, such that your model fits in your machine. So the only reason that is going to drive the way the model is built is like, I want to have the biggest model that I can on my machine and as deepest as I can, but that's going to fit my hardware. Okay. Well, so everybody has a kind of good understanding of the picture. Okay. So now I can wonder, okay, cool. How does it work? First clue. So if you check the first layer of the neural network, like here, there are a spatial resolution of size 11 by 11. And you see that the filters are pretty much structures. So you see that there are many filters that looks like localized wavelets in some sense. You see that there are some purely black and white filters, which means that they're just going to act on the image contrast. Yes?
So what you show is a result of the after running your neural network.
Yep.
This is after running the neural network that you get the first layer, which is like that?
Yep, absolutely,
okay.
Absolutely. What you see here is a collection of filters that is learned on ImageNet, and that does correspond to the first layer. So which is again of size 3 by 11 by 11, so that's why you can visualize the images. And this kind of strategy is not possible to use it in deeper layer because the reason is on the first layer you have access to the topology of the input, right? So you can say what a channel means, which is here a color, and you have access to that, and you can recombine the channel, and then you can visualize them. You cannot make these kind of things in any inner layer except maybe the final layer because it has an explicit goal, which is to separate the different classes. So if you look at those filters, so as I said, they are pretty structured, so they are rotated, rescaled. There are also some colored filters that look like more some kind of blobs. But like if you look at them more carefully, you see that most of them are conjugated by opposite colors, right? Like magenta and green, blue and yellow, cyan and orange, these kind of things. So you see that there is sort of structures. And in terms of like vision and colors, this completely makes sense because like the eyes is super sensitive to conjugated colors. So that makes sense. And so now that I have sort of reviewed the engineering point of view, which is how you train a neural network, what kind of, so I haven't done any zoo, which is like I could have discussed like what is a VGG, zoo of model. I could have discussed what is a VGG, pardon, what is a ResNet, what is it's called like a LoNet, or all these kind of models. I just want to see now like deep neural network is a kind of big black box with some cascade of layers. And I will not discuss any specific details of the architecture. So there will be no discussion about like what is the ResNet of these kind of things later. So what happens if we try to understand what is performed, what kind of operations are performed by the neural network? So first thing, so as I said, when we were looking at those filters, there are a lot of structure. So I mean, the first reflex you could have when you get those filters is like, okay, great. A simple model seems to be, that looks like pretty much some gabors, right? So what is a gabor? It's a filter which is defined by a scale, by a central frequency, and a rotation matrix. So once you have constructed this model that comes from the PhD of a colleague, you can have a nice map that shows you the distribution of the filters in the first layer. So you see that they're kind of uniformly distributed across like gamma frequencies. So here there are two scales. There is the first scale, then you dilate the first scale by a factor 2, so you get the second scale. And then you dilate it again by a factor 2, which explains why here it's like 2, 4, and 8. And so what you see is that they're even, the filters frequency are evenly distributed. And actually, if you check the scale of a filter which has a frequency which is slightly outside the circle, you could verify that actually the scale is slightly larger, slightly expanded, which means that it has really there is really like a multi-scale structure which is implemented by this first layer of analysis. So this is a bit surprising. Because there is no specific reason, there is no criterion that that requires a neural network to be like, yeah, I'm going to implement something very close to a Wavelet transform. And now there is something you can do if you go like slightly deeper in the model. You can take your filters in the second layer. You can assume that they're going to be written as a sum of separable filters. And you can try to find a low-rank approximation of your filters as a sum of separable filters. And because the first layer had an explicit topology, then at a given spatial location, you can figure out like at a given spatial location in the second layer to which frequency it would have correspond to the first layer, and then you can get the contrast of this filter. And you end up with those nice images which are a visualization of the filters in the second layer. So here you see many filters which looks like, it looks like they're kind of selective to some orientation. some of them looks like just low pass filter. Like it seems they're just doing an averaging. So some others that just look like noise. So it's a bit unclear what is done in it. But like, it means that still, if there are few layers, we can have some guess on what is implemented by the neural network. All right. So, as I said, if you want to, so the neural network, like we see that there is some kind of structure, some kind of geometry which is present in it. But like, again, there's a problem that the neural network has to address in a supervised classification task is to build a representation that is going to separate your data. So it means that the neural network needs to build a representation that is going to be regular, right? So by regular, I mean that two closed representations should actually have the same label. And so this notion of regularity can be like some geometric regularity. So as I said, for example, to be invariant to some group variability, those kind of things. Or this regularity in this sense, like two representations are close implies that two labels are close. And so it's necessary that the neural network both reduce the size of the space, because at the end of the day, you're going to end up with a single label. But also, it must not contract too much. Because if you contract too much, well, you know, classes are going to collapse, and then you will not be able to distinguish two different samples. So people have hypothesized that there might be a low-dimensional manifold hypothesis that could explain how the neural networks are working. So the main issue is that if you take a low-dimensional manifold, if you're in dimension beyond that 6, you cannot really estimate the points on your data manifold, which means that, I mean, there is a clear curse of dimensionality. You would need like billions and billions and billions of points to actually estimate the manifold of images if you don't have any additional prior. And maybe this kind of ideas like my data are going to live on a low-dimensional manifold, which would explain how you can build a regular representation, because then the representation will inherit the regularity of the manifold of the data. So this can be true maybe for data sets like MNIST, which are super small. And actually, if you try to solve those data sets with some kernel method, it's going to work, which implies that Euclidean metric is meaningful. And thus the data set is low-dimensional. But this is not the case if, for example, in your data set, there are many high-dimensional deformations, because deformations are so super high-dimensional objects. And you don't really know what will happen if this kind of variability is present in your data set, because in this case, you know that your data set is not in a low-dimensional manifold, and actually in images, deformations are kind of like, you know, everywhere. However, if you look at the features which are implemented in a deep neural network, you can parameterize some operator, like for example, changing a color or changing the lighting of your data, or changing the scale of your data. And in this case, because you have a low-dimensional parameterization, you will see a low-dimensional manifold, right? Because if you have something which is, for example, the rotation depends upon a single parameter. So, of course, if you apply a rotation to your data, you will see an orbit which is of dimension 1. However, the nice thing is that this kind of observation is going to be consistent across data, which means that if you apply a rotation to an object, in general, and I'm saying in general, the orbit of the rotation will be similar, which means that there is a kind of linearization phenomenon which might occur for some type of variabilities, right? Probably something where it's even more clear. It's with words. So for example, if you apply some deep neural network techniques on words, and you look at man, woman, king, and queen, it will be exactly the same direction that will transform a male word into a female word. I'm not sure it's a good way to phrase it, but I'm sorry. It's going to be about the same with the verb tense. It's going to be the same with the country capital of the words. And so it means that there is at least a linearization. I'm not going to claim that the data are in some low-dimensional manifold, because you will need more experiments to verify that. But actually, it's clear that there is something which is linearized. There is a direction of the space which indicates, which is meaningful. So this hypothesis of a kind of progressive manifold, which is built by the representation, it sounds a bit like kind of accurate, but again, this is experimental. And it's a bit difficult to figure evidences of this, right? Because if you don't have the good a priori as a person, if you didn't know in advance that you wanted to look at, to get this phenomenon, you will not be able to guess it, right? If you don't know in advance the structure, and we know it because we're human and we already organize those features in our head, if we don't know it in advance, it will be hard to guess this structure, right? Then people have tried to study the neural network through the scope of neurons. So here you're okay, I'm going to assume that I got a neuron in my neural network, which is an activation of one of the feature map. And what people have noticed is that a direction of the space in the space of representation has a semantic meaning. So it means that, for example, you have a direction for flowers, you might have a direction for round objects, for dogs, and kind of things. Now, so in this case, people were using a specific neuron, so it means a vector of 0 and 1. But actually, if you take any random direction of your neural network, most of them actually have a semantic meaning. So it means that the concept of neuron is pretty ill-defined. So it's not a good way to think of what is implemented by the neural network. All right? So we know that there is some kind of linearization phenomenon in the manifold of the data. We're not really sure that the specific direction of the representation are meaningful. And so one way to think conceptually of that is to assume that the neural network will try to flatten the level space, the level set of the supervised classification task. So in some sense, it means that at the beginning you have something which is a bit messy, and then you like to end up with a very nice Euclidean structure, something which is super smooth, and that will behave nicely locally. So that sounds great, but one can wonder, hey, how can we do that? Actually, there is a nice property which is Ghetto differentiability. And the idea is that if you Lipschitz with respect to a transformation, then you're gonna be weakly differentiable. In this case, you know that with a simple projection, you can remove the variability. So there might be a way to implement this notion of flattening thanks to this notion of weak differentiability. And the main issue again is that it's super difficult to exhibit such operator. So you can do it with translations, you might do it with deformations, but going beyond this, those simple transformations which have an explicit formula, it's a bit difficult. However, we can wonder, okay, great. So if we flatten the space, there should be a way to measure that. And actually, if you try to measure, for example, the linear separability or the dimension of your features, what you can observe numerically is that progressively, your neural network will progressively linearly separate the data. And they will be more smooth. Because if you apply, for example, a nearest neighbor on your data at the subsequent layers, so what you see here is the accuracy of a nearest neighbor or a linear SVM at different depth of a size of a depth 12 neural network. What you see is that those accuracy are improving. So it means that progressively, first, the Euclidean distance is more meaningful because a nearest neighbor would work only if the distance becomes more meaningful. And applying like SVM also improve progressively, which means that those phenomena of like linearization of the level set are occurring. So it's not a proof that there is an explicit flattening of the space. However, empirically, it's measured. So it's really unclear how we can explain this phenomenon. And the main reason is that we don't know what is optimized by the neural network. Okay. So now on a completely different page, there are some interesting like phenomenon with the adversary examples. So I'm sure you have seen those pictures where you slightly modify a given image, you perturbate it, you feed it to your neural network, and suddenly the prediction is going to screw up. And the main reason that neural networks are super sensitive to noise, and the reason why they are sensitive to noise is that there is a cascade of operator, which is Lipschitz, and the Lipschitz constants are locally super high. And so if they're high, it means that a small perturbation can actually completely change the behavior of your classifier. And in fact, you can even find some more universal type of perturbation. You can prove, numerically you can build, you can build some vectors which are going to perturbate any input of your data set and completely change the prediction of your classifier. It's a bit surprising because it means that for a given model there is a universal perturbation of the model that will change its output. And locally it seems clear because of the Lipschitz constant, but claiming that there is a direction which is common to any samples is quite surprising. Then for someone who was working in vision, people have also shown that the spatial mixing the spatial location is not important for discriminating a signal. So it means that if you get an image and you look at your image just locally and you try to classify it just with some neighborhood patches, if you do that on your image, then you can still classify it. So it means that, and it's called a backnet, and it means that neural network for having good performance do not need the context of the patch of an image, which is again a bit surprising. Some people, they have tried to reconstruct what is present in a layer, and so the way they did it is like you try to train a neural network to reconstruct from a given layer its input. So the way people have tried to solve this kind of question is again with a neural network. So what you see that with depth, the deeper you go in the layer of that you try to reconstruct, the more blurry are the images. And this is actually super logical because like there are some pooling and downsampling operators that are going to progressively smooth your signal. And so, after several layers of smoothing, then it's very difficult to recover the original frequency. It's literally an inverse problem, and so it's quite difficult to inverse the output of a neural network. But then it can give us some ideas of the mechanism which is implemented by the neural network. Could be like maybe that progressively a given layer will try to discard some information which is related to the input sample and actually keep the information which is related to the class. And so people have proposed to use something called the information bottleneck. And so there is this idea that if you apply progressively some layers on some input, you're going to compress the information related to the input signal. And on the contrary, you would like to reveal the class of your signal. And so people propose, so it's in particular like Tishby, he proposed to try to maximize the information to try to train in a greedy manner every layer of a neural network, and each layer should progressively maximize information related to a label, but actually reduce the information which is related to the layer before. So it kind of makes sense, this principle, and it's quite appealing, right? Because that's logically what we should do if you have if you have some picture of a cat or of a dog. You would like to progressively remove what is not important for classifying your image as a cat and keep what is important for classifying your image as a cat. That makes sense. But actually, the main issue is that it's super easy to build some invertible neural networks. And so if the neural network is invertible, everything here is an inequality. So it doesn't make any sense to use this principle to try to explain how the neural network is working. So I've been working on this kind of ideas, and so the principle is quite simple. So you take a feature, you split it in two, you apply something very close to a lifting scheme on your features. This step will be invertible. But then you get again two features, you exchange them, and this way you get something called, we call it like an IREVnet. And so the nice property of the neural network is that from the input to the output, you can reconstruct everything. And actually, it's very insightful to look at the reconstruction of the images. So for example, if we, at first I told you, yeah, there might be like some linearization phenomena that are occurring. That's great. But if that was true, for example, assume that the neural network should linearize deformations. So in this case, if you take like two images which are deformed, this is, for example, what is here on the first row, then their reconstruction, if you take like two convex paths between those images, the convex path should behave nicely, right? This is actually what linearization means. It would mean that locally, you should behave like an Euclidean space. And so what you see here is the interpolation of the reconstruction between two images. So in the feature space, you fix two features, you reconstruct the element of the path, and you get the original images, thanks to the fact that the neural network is invertible. So the three rows correspond to signals which have been deformed. So we see that there is absolutely no structures. The signal is super unstable, so clearly there is no linearization. This is the same with rotations. So here you see a face which is rotated, and again, there is no such phenomenon. One sees a signal which is a bit like, which is completely unstable. Then even like two images which are almost superposed does not behave well with respect to the linearization phenomenon. And so this is quite surprising. Okay. So now I'm going to discuss some more exciting works about invariant representations. So what I tried to show you, like in the first section, was how to implement the neural network, like how to train them, and some kind of intuition on the model which are used, the tasks you can solve. Then I kind of tried to show you what you can empirically guess on the interpretability of your neural network. And now I'm going to discuss some ideas I tried to propagate through those slides, is this idea of invariance. And in particular, I will discuss the scattering transform. So if you take those two signals, if you take the L2 norm of those two signals, we agree they are super far from each other, right? You have, for example, on the top image, you have like two grids, which are translated. If you take directly the L2 norm between those two grids, those two signals will be orthogonal, so their L2 norm is equal to 2, right? It's going to be the same for this feature. So here I assume that I've encoded my image with a feature which is covariant with rotation. Again, if I get the L2 norm between those two signals, they will be super far from each other. So has someone an idea of how to make them closer? averaging. If you sum the pixels on the top image, we agree the sum of the two images will be equal, right? And actually, they will be invariant to the action of translation, right? It's about the same like with the other descriptor, but like here you would need to average along the rotations. But thanks to averaging, we can build invariance, right? Okay. So I'm going to use, I don't know if you're all familiar with the Fourier transform. I'm sure you do. But like if you really have all the properties which are commonly used, but like, for example, if you do the conversion of two signals, you know that the Fourier transform is equal to the product of the Fourier transform of each signals. So I'm going to use that widely, so I prefer to write it down just to be sure that everybody have it. So it's Fourier transform of a signal that I can write this way. Where are these? There is another property which is dilation. So if I write like so for a given like scale, a real number a, if I dilate my function x by a, and I renormalize it, then we know that and then there's also the notion of like translation. So you know that if you translate a signal, so here, if I translate a signal by A, you know that the Fourier transform is and what else? And there's also the Perceval inequality. Right. So I'm going to use that a lot, and if you're not used with the wavelets and this kind of thing or processing, it might become a bit difficult. Right. So, right. For example, say you want to achieve like translation invariance. What's the simplest way to do it? So given like this formula here, you could take the modulus of the Fourier transform, right? Because if you take the modulus here, you're going to remove the phase, and in this case, the complete invariant to translation. Sounds good. However, now the issue is stability of this operator. So if you consider a deformation, and if you consider, for example, this signal, so here a deformation is like I'm getting a small perturbation of my coordinates, which is defined by a small diffeomorphism. So I'm going to measure small in terms of the infinite norm of tau and its Jacobian. If I take a small diffeomorphism, we can show that the modulus of the Fourier transform is not stable to small deformation. And the simplest way is to take, to prove that, simplest way is to take an example. So if you get this signal, which is a nicely centered Gaussian in the frequency omega 0, and if you take this deformation, which is simply 1 minus s of the dilation, a rescaling of the spatial coordinate. If you take this signal, then you can prove that the Fourier transform of those two signals are going to be distant, quite distant, because actually the 1 minus s is going to behave as a rescaling of the central frequency. And in this case, if you take the L2 norm between those two representations, they will be equal about to the central frequency of your signal multiplied by the deformation. So basically, the norm of the Jacobian of the deformation. So this is bad. Why? Because it means that you're not stable to deformation, right? because then if you let omega 0 going to infinity, then you see that it's not possible to find the Lipschitz constant, and this is not going to work, right? Okay, so our goal now is to define a representation which is invariant with respect to translations. Okay, so now if we dig a bit like in the convolutional neural networks, so the representation I will discuss has its foundations in deep neural networks. If you take like an operator L, you say that L is covariant with W, so for example, convolutions are covariant with the action of translation if and only if the two operators commute, right? So if you have a signal, you translate your signal, you convolve it with some signal, it's exactly the same thing as if you had convolved your signal and then translate it, right? Okay. Then there is this notion of invariance. So you will say that an operator A is invariant with respect to some variability L if and only if AL equal A, right? So if we're given a cascade of operator, we can easily build an invariant. How? Take your representation, you write it as a cascade of covariant operators, and at the end of your representation, you put an invariant operator. Okay, so in this case, well, if you apply your variability at the input of your representation, the variability is going to commute, hence it's going to be next to the invariant operator. In this case, it achieves an invariance, right? Everybody's clear with this mechanism? Awesome. And then there is like, it's completely possible to have some operators that only approximately commute with the action of another operator, right? So just one example, for example, deformation. If you deform your signal, the convolution of the deformation will clearly not be equal to the convolution of the deformation, right? Okay. Well, except if the deformation is a translation, right? Okay, well, it's not very interesting. In fact, this idea, at some point I mentioned something called a pooling. And a pooling, it's literally a small local averaging. So you take like, for a given spatial position, so say we work in 1D, a pooling will be simply the averaging of like two neighborhood locations. So it's literally like creating some invariance, some local invariance, some approximate invariance. And so neural networks are very often a cascade of linear operator, nonlinearity, and those pooling operators that progressively build some invariance. Of course, a Wavelet transform satisfies this kind of properties. And in fact, something that is going to justify the fact that people are using nonlinearity, pointwise nonlinearity in deep neural networks is the following. You can prove that a pointwise nonlinearity is the only operator that does commute with the action of deformations, right? And so this is proved in the PhD of Joan Bruna. And so it's literally this idea that if you apply a deformation on your signal, if you apply nonlinearity on it, you see that it's Kerry commuting. I mean, it's almost, by definition, it's almost a tautology. Reciprocally, you can prove that this is the only nonlinearity that is commuting with a pointwise nonlinearity is the only operator that is commuting with the action of deformation. So this is nice, because it really does explain why there is a structure in the neural networks, right? So progressively, we start to understand why there are structures this way, why there is some pooling, why there are some pointwise nonlinearities. So now, going to discuss slightly like the notion of wavelets. So who is familiar with wavelets? Who is not familiar with wavelets? Will be easier. Okay, well, so it will be for you. So a wavelet, it's often used to obtain some sparse representation. It's an L2 operator which has a zero sum. In the case of images, you very often show them such that they satisfy, they minimize the Heisenberg presimple, which means that they have to be well localized in space and well localized in frequency. You're going to rotate them, delay them, and from that you will get what is called a Wavelet Transform. And in general, because you want to be selective to some orientations, the kind of images, you're going to show them non-isotropic. So it means that they look like blobs locally. And for example, the wavelets which are used in the scattering transform, it's some Gabor wavelets. So here what you see is the pictures where the phase is given by the color. Because like if you think about it like it's a circular shift. And the amplitude gives the contrast of the image gives the amplitude of the signal. So it looks like kind of a flower in some sense. And so wavelets are typically used because of their sparse properties. So it means that if you get a signal, because your signal, for example, can be well approximated by a cartoon model, you get your Wavelet transform of your signal, it's going to be sparse because locally everything will be simply some edges, there'll be some lights and kind of things, and which is well approximated by your Wavelet transform. However, here, it's another property that is interesting in the case of those wavelets. It's the localization that is going to be very interesting. This idea that we're going to pick some filters which are well centered on a certain frequencies, and then if you translate the convolution of a sum signal with those filters, we'll get a phase multiplication. And so in the lab tomorrow, I mean, there will be a formal proof of this fact. But actually, so hope everybody has that in mind now. Yeah, you're right. Forgot about that. Right. Okay. Right. So we get this property because the filter is well localized. So everybody agrees that this is quite a definition of being localized. So what is if I multiply my if I convolve, some translated signal with this filter, what do we get? So sorry. We get like a translation corresponds to a phase multiplication in the Fourier domain, right? But now I'm going to use the localization property, right? And sometimes you can think of it as if like in Fourier, if you differentiate a signal, you will get a multiplication by omega, right? And in fact, the fact that you get an exponential here is completely linked to this. It's a Taylor expansion, if you think about it. In other words, the infinitesimal generator of the translation is the derivation, because the exponential of the derivation is equal to a translation. That's what Taylor expansion tells you, right? Okay. So this is great because I'm going to use this expression here. And actually, like from this formula, we get So it's super basic. It just gives you an intuition of why we're going to build invariance thanks to the localization property. And actually, it's super crucial. If you don't use this property on the wavelet, it's completely useless. Sorry. And so again, we go back in the spatial domain and okay, I hope it's larger, I don't know. And so you get that. So in other words, if you translate a signal, you convolve it with well-localized filters, you get a phase multiplication. So why is it nice? Someone get an idea? No? So, let's proof. It's great because if you apply a modulus on your signal, what we just get there is the fact that a modulus will demodulate your signal. Yeah, don't know if it's better. Sorry. If you apply a modulus, you will get an approximate invariant with respect to translation. And I guess I'm going to be done for this. We have to do a break at 10:30?
Yes.
Okay. Right. So if you apply the modulus on the resistant convolution, you get an approximate invariant. This is great because what we wanted to achieve is invariance with respect to translation. And so what I will discuss next is actually how to get an invariant representation which is discriminative and that will really look like a neural network. Okay, so thanks.
Any questions before the coffee break? Yes.
Thank you very much. So just to be quite clear on this calculus.
Intuitive, yeah.
Yeah. If you the figure on the right, you're just saying that the only omega that is going to count is around omega 0.
Absolutely.
So you use a small frequency window, I guess. That's
Absolutely.
Okay.
So actually, the statement can be made super formal by being like, outside an epsilon 0 ball around my omega 0, okay, I'm going to be small, and then you get it.
Okay.
So, really, the reason which is key, and that's why I wanted to do the proof, is the fact that here, in Fourier, you must read the derivation. That actually, what tells those equations. And that's Fourier, literally. That's a derivation, literally. You get, the fact that, in other words, just to be sure everybody got it, but, you get literally a Taylor expansion. Pardon. And this is equal to a translation by, if I add, of course, a puissance n, this is equal to a translation by a. It's a bit informal, and that's how physicists, if I'm correct, if it's written by physicists, but there is really this idea that a translation corresponds to an exponential of the derivation. It's literally a Lie group, which is generated by whose infinitesimal generator is the derivation, the translation group. Well, I answered your question.
Yes, but before, just this part wasn't really. I didn't get why the derivative, the exponential of derivative operator was a translation.
So, if you take a smooth signal, x of u plus a, it's equal. If you apply a Taylor expansion, this is the sum of their derivative applied in u of a power n over factorial n, right? Mm-hmm. It's just a Taylor expansion. Except if I screw up, but I don't think so. And what you recognize here is an exponential, right? Okay. Well, so actually you can make this super formal, and you can work with the translation group, you can derive an exponential because actually the derivation is a linear operator. And using this fact, I mean, you see that what we're claiming here is actually that a phase multiplication is very close to be a displacement along a small group of translations. You get it? Cool.
Thanks.
Other question?
Sorry, I don't understand how you switch from the equality in the Fourier domain to the modulus in the space domain.
Where?
So you derive the equality x, the Fourier transform of xa convoluted with psi.
Yeah.
Is more or less equal to the how you explain it with the exponential times the Fourier transform of the convolution, and then you say this means that I have the modulus of the convolution xa convoluted with psi, which is more or less the modulus of.
Right. So actually, it's all written here. So if you take the inverse Fourier transform of those two signals, since this is a constant, and here you had the translation, I mean, and since the Fourier transform is almost an involution, if you take the inverse Fourier transform here, you get back like a phase multiplication times x convolved with psi. Here you get like the translation of x convolved with psi. So if you apply the modulus, yeah. But actually, it can be made formal. I mean, like literally tomorrow in the notebook, like there's.
Okay, I didn't see that the omega 0 was fixed. So.
Right. So the only interest of this derivation is really to get this intuition that here the phase multiplication is really a displacement on a group. Like it's just for this reason.